Today we're going to continue talking about light. Specifically, last time we talked about all the different kinds of light, right? Or the last few times. But what we're going to be talking about today is now, what can the light tell you? Okay, what if we look at an object, other than just being able to see it, what can we learn about that object based on the light that's coming to us? Especially if we use all of these invisible types of light to help give us even more information. Okay, so here's specifically what we're going to be learning. So, 3 things the spectrum can tell us. Okay, and there's a whole bunch of information we can learn about objects out there, but we're going to be learning 3 major things in this chapter. And that's the last 3 things that we're going to learn about before the first test. Okay, so we'll see how long this takes us. All right, so first up, before we can even talk about what the 3 things are, we need to know what is a spectrum. Okay, so let's talk about what a spectrum is, and then we'll come back and start talking about the 3 things that it can tell us. Okay, so let me just kind of scoot this over for a second. Let's figure out what a spectrum is. Let me put it in words first. A spectrum is just a fancy way to say the pattern of light that an object gives off. Okay? A spectrum is the pattern of light an object gives off. Okay? And that might be kind of vague. Okay? So let me show you one of the ways that you can show the spectrum of an object. The most commonly used way is a graph. Okay, so let's just draw a really quick graph real quick. Just a normal old graph. Okay. And on this graph, on the x-axis, we have this. Okay. Does anybody remember what that symbol stands for? Does anybody know? Let me zoom in a little bit here. Does anybody remember what this symbol right here stands for? We talked about it over the past few times. So that it's called lambda, but what concept does it stand for? Wavelength. Wavelength. That's correct. Wavelength is what it stands for. Okay? So, on this axis down here, we have wavelength increasing in that direction. Okay? We have wavelength increasing in that direction. So big wavelengths are on the right, small wavelengths are on the left. So here's my question. Where would radio light be on this graph? Would radio light be in the middle, on the left, or on the right? That's your choices. Where would radio be? Okay? And remember, wavelength is increasing as you go to the right. So you have to think of the size of the wavelength of radio light, okay? It would be on the right. That's correct. It would be on the right. And that's because, remember, radio light was the longest kind of light. So radio would be over here, visible would be in the middle of the graph, and then gamma rays would be way over here on the smallest wavelengths. Remember, longer wavelengths mean lower energies. Shorter wavelengths mean higher energies. So, radio's on the right, gamma's on the left, and everything else is in between. Okay? Now, on this axis, we have something I'm going to label with a capital I. And that just stands for intensity. Okay? Intensity. Basically, brightness, right? So, this is basically a graph that tells you how bright every wavelength is from that object. Okay, so a spectrum, you can think of it as a graph of intensity of every wavelength of that object. So the brighter, like if an object was giving off a lot of gamma rays, this part of the graph would be really tall. If it was giving off a lot of radio, this part would be really tall. And if it was giving off a lot of visible, the middle would be really tall. Okay? So typically, A typical object might have a spectrum that looks like this. Sort of a single hill shape, okay? So this particular object, this one right here that I just drew, if this was what the graph looked like, here's my question. Is this object giving off a lot of gamma rays? Is this object right here giving off a lot of gamma rays? Yes or no? And if it's giving off a lot of gamma rays, the intensity would be really high in the gamma region, right? So no, that's correct. No, this one is not giving off a lot of gamma rays because the gamma part of the graph has a very low intensity. It's also not giving off a lot of radio, okay? But this particular object is giving off at least a little bit of every type of wavelength that there is. At least a little bit, right? Yeah, okay. So, keep that in mind. Actually, here's where I should go. There's actually only one type of object that makes a spectrum that's a perfect single hill like this, okay? And we can think of that as a perfect light, okay? An absolutely perfect light will give off at least a little bit of every type of wavelength. Not necessarily in the same amount, but at least a little bit of everything, okay? And of course, we get a freeze already. Oh, we're off to a good start. And I'm bringing that up because this is not the only way that you can show a spectrum, okay? This is not the only way that you can show a spectrum. To help you understand what I'm trying to talk about right here, let me explain how we get the spectrum. That's a very good question. Someone is asking, is this graph for one specific light or all light that we know? Okay, so this is the spectrum of one object where we have split the light into all of the color, all of the wavelengths that object is giving off, okay? And we put it on a graph of all known wavelengths. And if that particular object was giving off a lot of gamma rays, then when we pick up the gamma rays, this part of the graph would show very high. So the spectrum is of an object, and this graph is just telling us which wavelengths it's giving off and how bright each one is, okay? And how do we do that? When we look at an object, you don't just see one wavelength at a time. You see everything mixed together, right? You see everything mixed together. So in order to make this graph, what we have to do is we have to take the light that object's giving off and split it so that we can see how bright each one is, okay? So let me just show you a picture from the book real quick. This will help explain what I'm trying to say. This is not the picture I wanted. This is the picture I wanted. So right here, imagine that this right here is a perfect light, okay? Imagine that's a perfect light. One way that we can split the light is by passing it through a prism or a little piece of glass like this. And that's going to cause all of the different colors to bend different amounts. Does anybody remember what that's called? Does anybody remember what this process is called when we take that light and bend it? Take that light and bend it through a substance? That one we've seen a few times now. Yeah, that's refraction. That's refraction. So what we can do, because we don't want all of the light to be mixed together, we can refract that light or do other processes that do basically the same thing. And because every color in that original light bends a different amount, you're going to end up splitting that light into essentially a rainbow. All right? So if this is a perfect light source, then that complete rainbow will be present, right? If it's not perfect, like let's say this object didn't have any yellow light in it, when we split it into this rainbow, then the yellow right here would just be black. It would be missing, right? So only a perfect light source produces a perfect rainbow. And right here, this is another way to show the spectrum of that object. This is actually what the photograph of the spectrum actually looks like when we actually take the data. So if this object, for example, was giving off way more red than the other colors, then the red part would be the brightest part of the rainbow. So that means this picture is telling us how bright each wavelength is, right? And what they've done here is they've taken this rainbow photograph and turned it into a graph like I was talking about just a second ago. See, wavelength versus intensity. So both of these are two ways to show the spectrum of an object. And we can actually extend it into the invisible types of light in both directions if we have a good camera, okay? So, here we go. If you have an absolutely perfect light source that has every single color present, including all the invisible ones, then your graph is going to be nice and smooth, okay? Like the ones I've been drawing. And if that's the case, we call that kind of spectrum a continuous spectrum, okay? A continuous spectrum. So the only type of object that actually makes a perfectly smooth, continuous spectrum is a perfect light source. Okay? Now, here's my question. When we look at objects out in space, how many of them are probably perfect? How many of the objects in space are probably perfect light sources? If you were to guess. Yeah, very few. None is actually the correct answer. It's none. So basically, nothing is ever going to make an actual perfect rainbow. There's always going to be something missing in every natural object. So continuous spectrums are kind of like the ideal that we compare things to, but we never actually see them. We actually see two other kinds of spectrum, which we'll talk about in a little bit. Okay, so that's the basics on what a spectrum is. Okay, it's just a graph. It's just a way to display how bright every color is coming from an object. So what we're going to be learning today is, what can we learn about the original object based on the shape of this, okay?